All right. Hello. Um, just make sure I got the right Google Meet link up there. I think I do, but it should end in NZZ. Uh-oh. There's an extra letter at the end of that. Let me just copy this one more time. I don't know where that extra letter came from. Let's fix this. There we go. What about the other one? Okay, it's good in the other section. Remember, please mute your mic if you're not currently speaking. Otherwise, it's going to create echo. Like that. All right. So let's go ahead and get started here. Let's get this countdown out of the way. All right. So put up a few problems, mostly about the gradient stuff, because I think that's important to understand sort of what the gradient's doing here. So yeah, just a reminder, if you're watching and you're not in the Google Meet room, I did somehow get an accidental wrong letter at the end of it. All right. So let's look at these problems here. So these are mostly directional derivative problems. Right. So what we want to do is compute the gradient, evaluate the gradient at some point, and find the rate of change, which is the directional derivative. Oh, I have a camera that I should turn on. Let's do that. Hello. All right. So for the first problem, right, our function is f of xyz equals x squared yz minus xyz cubed. All right, so let's first find the gradient of this thing. Right? Remember, the gradient of f is just sort of collect all of the first derivatives together. So do the derivative with respect to the first variable x. We have 2xyz minus derivative with respect to x, so yz cubed, comma. Take the derivative with respect to y, which is going to be x squared z minus xz cubed. And then do the derivative with respect to z, which is x squared y minus 3xyz squared. All right. Okay, and that's it for part A. Part B is we want to evaluate this gradient at the point p equals 2 minus 1, 1. Right? So we're asking, well, what is gradient f of 2 minus 1 and 1? Right, no big mystery here. Just plug in these numbers for x, y, and z. Right? So, see, when we plug that in, we're going to get negative 4 plus 1. Sorry, 1 second. Okay. Plug numbers in here, we're going to get 4 minus 2. And plug numbers in here, and we're going to get lots of sneezes today, apparently. We're going to get actually negative 4 plus 6. All right, so this is -3, 2, 2. Hopefully I've not messed up any computation there. All right, so that's the gradient at this point. The directional derivative. All right. One thing you want to make sure of here is that v is a unit vector, because when we do the directional derivative, we need to take the derivative or the dot product with a unit vector, right? Because we only want to know what is the rate of change in the direction of that vector. We don't want the length of the vector, the magnitude of the vector, to affect that. So we do need to make sure that it's a unit. All right, so if we check that, we're going to get, let's see, 0 plus 16 over 25 plus 9 over 25. And this works out to be, well, 25 over 25, which is 1. So it's a unit vector. So that means that the directional derivative, the derivative in the direction of v of f at the point 2 minus 1, 1, this is just going to be the gradient of f at that point, dot product with v. All right? So let's go ahead and compute this. We need both parts here. Oh, sorry, we need this. So -3, 2, and 2. Dot product with v, which is 0, 4/5, -3/5. If we do this dot product, we get 0 plus 8/5 minus 6/5. So that's 2 over 5. So this is just, saying if we start walking in the same direction that v is pointing, this is sort of how fast, if we think of f as an altitude function, that I guess works a little less when it's 3 variables, but just sort of if we move in the direction of this vector, this is how fast the function's changing. Right, so a good application of this kind of idea, an easy application of it is, imagine your function's giving you, the temperature at every point in space. And then this directional derivative will say, if we move in this direction over here, how is the temperature changing? Right? At what rate is the temperature? Okay. Any questions about this one? All right here. All right, cool. So let's look at the next problem here. I meant to write a C here. The next problem is f of uv equals u squared e to the minus v. Okay. Let's do this in the same order. First part is take the gradient of this. The gradient of f. We differentiate again with respect to the, in the same order as the variables here. So with respect to u, then with respect to v. So differentiate this with respect to u. We have 2u e to the minus v. Right? And then differentiate with respect to v, and we have -u squared e to the minus v. Right? All right. And now we want the gradient at the point 3, 0. So gradient of f at 3, 0. Just plug that stuff in. And here we're going to get 2 times 3 times 1. And here -3 squared times 1. So 6 minus 9. Right. And then finally, let's look at, we want the directional derivative in the direction of v equals 3i plus 4j. Right. Now, again, we want to check that, well, is this a unit vector, right, if we compute the magnitude of this vector here, you're going to wind up with 5. Right? And actually, I just now realized how close this vector was to the one for problem 1 here. So since this has magnitude 5, we need to make it a unit vector first. Right? This is what I like to call v hat, and this is just, v over magnitude of v. So this turns into 3/5 I plus 4/5 j. Right? Now once we fix that, we can find the directional derivative. Again, we want to find the directional derivative, the rate of change in the direction of this vector. So we need to make sure it's a unit vector. So d v hat, make that look more like a hat. V hat of f at 3, 0. This is, again, gradient of f at 3, 0, dot product with v hat, sorry. So was it 6 minus 9, dot product, 3/5, 4/5. And now we just compute that. So 18 over 5 minus 36 over 5, which, really interesting, happens to be exactly minus 18 over 5. There we go. Any questions about that? Where did the 4/5 in the last problem? Problem 2, right? Right here, this one. Problem 1. Let's see, 4/5. So that vector. So the vector v here, I didn't actually write it down on the page. V is, well, this thing right here. V is exactly this thing. So was there another 4/5 or? I think that's the only one, right? Oh, v is given in the problem. Right, the problem gives you f and then p and then v. So I didn't derive it at all. It's just there. Yeah, so that's a given quantity. Generally speaking, you have to have a vector beforehand to take the directional derivative in the direction of. Right? Cool. All right, just wanted to make sure we're on the same page here. All right, so let's go ahead and do the next part, problem 3. We got f of xyz equals xy squared arctangent of z. Right. So again, let's start by doing the gradient. And in fact, let me give you a minute to try out the gradient on your own first. I'll give you a minute to do that, and then I'll go ahead and compute it here. Right. So the first two derivatives, well, they're all actually not too bad here. Right? Only one thing has an x, so when we differentiate it, it goes away. Right? When we differentiate with respect to y, only this y squared takes the derivative. 2xy arctangent of z. And the derivative of arctangent, not a terribly difficult one. Right? It's 1 over 1 plus z squared. So we wind up with this as the final answer. So just as a reminder, derivative of arctangent important function to know. It's a great function, very useful for many applications. That camera just doesn't want to turn. It's determined to be there. All right. So now that we got that, let's go ahead and find the directional derivative. Or sorry, the gradient at the point 2, 1, 1. Right, so the gradient at 2, 1, 1 is, we just need to plug this stuff in. So really, we need to know what arctangent of 1 is. So remember, we're asking what angle would tangent output a 1. Right, so that would be pi over 4. Right, so here we have 1 times pi over 4. I'll even put the 1 squared there if you like. And then here we have 2 times 1 times another pi over 4. And here we have 2 times 1 squared over 1 plus 1 squared. So this is pi over 4. 2 pi. Nope, just pi. Just kidding. And this is 1. All right, so pi over 4, pi 1. So hopefully that's not too bad. All right, so think about the directional derivative here. In the direction of the vector 1, 1, 1. All right, so think about that for a second. See if you can work that one out. What I should look into is if I can freeze the video or the capture of my tablet here, and then I can work while you guys are working, and then I can just display the answer. Let's see if I can find that while you guys are doing this. I'll have to look into that. All right. So again, we want to make sure that we have a unit vector here. This thing is not a unit vector, right? In fact, the magnitude of this is square root of 3, right? So we need to make v hat, right? Which is just going to be 1 over root 3, 1 over root 3, 1 over root 3. You could also write this if you want, by the way. It's just 1 over root 3 times 1, 1, 1. Right? There's no issue at all in doing that. Okay. And so directional derivative in the direction of v at, is it 2, 1, 1? Yeah, 2, 1, 1. Oh, I totally forgot the f, didn't I? Directional derivative in the direction of v hat of f at 2, 1, 1. This is pi over 4, pi, 1, dot product with 1 over square root 3, 1, 1, 1. So that 1 over square root 3, remember from our vector properties from, way back, like first, second week of our second week of class. Sounds about right. We can just pull that constant all the way out and then do the dot product between the remaining thing. So pi over 4 plus pi plus 1. So the most simplified this is possibly going to get is, let's see, we'll have 5 pi over 4 plus 1. I mean, we can combine this together into one fraction, but there's, not really all that much more to write, really. So I'm going to just leave it like this. See? That's our answer. Any questions about these? This all look good. Okay. So, let's see, let's go on to the next problem here. So we're finding maximum rates of change in the next problem. Right. So remember, this idea of a maximum rate of change came down to looking at the formula for the dot product in its other expression, right? So, when we're doing a directional derivative of f at some point, we're looking at it as gradient of f dot product u, which, if you remember, we can write like this. And the whole idea of this came down to, well, this is always 1, so we can just ignore that. And the way we make this as large as possible is when cosine of theta is 1, because cosine only gets less than 1. So when theta is 0, that means these two vectors point in the exact same direction. Sorry. So they're not just parallel, but they're in the same direction exactly. All right. So, let's go ahead and work this out. So what we want to do is find the maximum rate of change of the function at the given point. So, well, let's see here. So f of xy is 4y square root of x at the point 1, 1, or 4, 1. Right? So to find the maximum rate of change, well, what it comes down to, if we look at this formula up here, it's just the magnitude of the gradient, and that's it. Right? So let's see here. So we need the gradient of f. Right? So when we differentiate this, we're going to get 2y over square root of x. Right? That's going to be the derivative of this with respect to x, and 4 square root of x when we differentiate with respect to y. Right? And then plug in 4, 1. And we get, let's see, this is going to be 1. This is going to be 8. And so the max rate of change this is always just the magnitude of the gradient And this is square root of 1 plus 64. Let's see, square root of 65. That's 5 times 13, so okay. That's as good as it's going to get. There's no way to simplify that square root. Right? So this is really all there is to it. You just find the gradient, evaluate it at the point, and take the magnitude. Right? But it's an important concept to remember. The computation of it is maybe less important than knowing, why the max rate of change is in the same direction as the gradient, right? And since that's true, that then means that the max rate of change happens to be the magnitude of the gradient. And again, that comes down to this formula up here. Because this part, I realize I'm covering this with my hand and it's not doing any good. But this part, this cosine, basically goes away. So, why don't you try the second one real quick? Take a second to try that, and yeah. All right. So here we have f of x, y, z equals x over y plus z. And we're doing this at 813. So gradient of f, when we differentiate this, we're going to get 1 over y plus z. Here we'll get negative x over y plus z squared. And interestingly enough, the third component should be exactly the same. Right? Okay. So that's our gradient there. And then plug in 813. And we're going to get, let's see, 1 over 4 minus 8 over 4 squared, and minus 8 over 4 squared, right? And so when we simplify this, we're going to have 1/4 minus a half minus a half. Right? And so the max rate of change again is still just the magnitude of the gradient at this point, which is 1 over 16 plus 1 over 4 plus 1 over 4, which is 9 over 16. So 3/4. Those numbers worked out quite nicely. Right? So how's that looking? Any questions about any of that? All right then. All right, so let's look at some of the more interesting problems here. The last two. Right, so the problem 3 is we want to come up with the equation of a tangent plane. all right, to this surface. It's x to the fourth, not x squared. So we got this surface here, which is 3x squared, y squared, z squared. Right, and we want the tangent plane at 1, 1, 1. Right? So remember, the key thing about the gradient is, the gradient is always perpendicular to any level sets of a function. So if it's a function of two variables and you have level curves, the gradient, if we graph that vector, is always perpendicular to those level curves, right? If it's a 3-variable function and we take a level surface of that, the gradient, anywhere we plot it, is going to be perpendicular to the surface at that point, right? So to get the equation of a plane, we need a normal vector, or something that's perpendicular to the plane, and we need a point. So of course, the point on the plane is going to be this one, because we want the plane to be tangent there. And since the gradient is perpendicular to the surface, the gradient then must be perpendicular to the tangent plane, because the tangent plane is supposed to capture sort of, what directions the surface moves in at that point. Right? So first things first, we need to recognize this as the level set of a function. So we'll call this capital F of x, y, z. And again, all we do, it's the same kind of thing that we did with like the implicit differentiation stuff. Just slam everything to one side. So x to the fourth plus y to the fourth plus z to the fourth minus 3x squared, y squared, z squared. Right? And the specific level surface we're interested in is when this would equal 0. Now that's not something, that number that equals 0 isn't something that's going to factor into our computation here, but nonetheless, it is the specific surface that we're looking at, right? So when we take the gradient of this function, right, we're going to have 4x cubed minus 6x y squared z squared. And then 4y cubed minus 6x squared yz squared. And 4z cubed minus 6x squared y squared z. Right. Okay. So now that we have that gradient, we want to attach that gradient to the surface at the specific point. Right? So we want to attach it at 1, 1, 1. Right, so this says, that gradient, that exists for any point x, y, z in space. We need to make sure we plug in a point that's actually on the surface. In particular, we want to plug in the point we want the tangent plane at. Right? So let's go ahead and plug that in. So if we plug this, so all of these variables are 1, so this is just 4 minus 6 everywhere. So minus 2, minus 2, minus 2. Right. Now the nice thing here is that we can always use any vector that's parallel to this to make the equation of our plane. Right? The length of that vector doesn't matter. So if you get something with, particularly nasty numbers, you can multiply or divide or, factor out the bad part of it and just keep the good part. So like here, I could factor out a negative or divide by -2 and just use 1, 1, 1, and that would be fine. So, okay. So the tangent plane, right, the tangent plane is basically gradient of f at 1, 1, 1, dot product with x minus 1, y minus 1, z minus 1 equals 0. right? The tangent plane is basically always going to take this form. And so let's compute that. We have -2, -2, -2, dot with x minus 1, y minus 1, z minus 1 equals 0. As with always, feel free to stop there. That would be perfectly fine. Or you can compute out this dot product if you like. So -2 x minus 1, -2 x or y minus 1, and -2 z minus 1. Let's see. And if you simplify this, you'll wind up with this. Let's see, this is going to be +6, so -6 over here. So the simplest form of this would be here. Right, that would be the simplest form of this plane. But again, I'm less interested in, like how well this can be simplified. I'm more interested in sort of, can you get to here? This is what I think is important. Right? This is what tells me that, you know that the gradient is the normal vector to the plane, and you know how to construct the plane. Okay. So, any questions about that at all? All right. I guess we have one more example here. This is kind of an interesting one as well. So problem 4, we have a paraboloid z equals x squared plus 3y squared, and a plane z equals x plus y plus 4, right? And these intersect in some curve C, right? So this intersection, actually, I'll bring up Mathematica and I'll plot that in a second here. But these intersect in a curve C. Right? So I guess maybe a quick sketch of sort of what this looks like. You have your paraboloid here. Oops. I drew this in the wrong way. Oh, what? It's fine. We'll live. Okay. So you have something like this, and then the plane is coming through, and it's going to hit this. Planes are impossible to draw. But the way it hits this is something like this. I don't know, this is hard to draw. But basically, you get some kind of like oval through the parabola that it cuts it slices into it with. I don't know, drawing planes is like super hard for me. So I'll show this in Mathematica in a second here. But the goal of this problem is we want to find the tangent line to C at what was the point? 217. Right? So that's the problem there. Go ahead and think about that problem for a second while I make up the picture in Mathematica real quick, and then I'll share that. All right. So let me switch over real quick and show you a not bad drawing of this. Right. So it looks something like this. So the orange one is the paraboloid here. And the blue one here, this is the plane. Right. So I have if I widen the box a bit, we can maybe see it a bit better here. Let's see. Okay. So here you can see this is a paraboloid here in orange, a plane there, and we get some kind of an intersection here. Now if I change this back to the right aspect ratio, you can see that the intersection is this oval here. And what we want to do is we want to find the tangent line at 217. Let's see. 217 is probably like this point right here. Right. So how do we do something like that? So since this, this curve, this intersection here of these two surfaces, it lies in both surfaces at the same time, we know that the curve is also perpendicular to both gradients, right? So we can use that knowledge to build our tangent vector, right? The direction vector for the tangent line. So let's switch back here. So how do we do this? Well, we're going to want to find the gradient for both of these. So we need to think of them as level surfaces. So we need two functions. F equals, again, just push everything to one side. So x squared plus 3y squared minus z equals 0. And g is x plus y plus 4 minus z equals 0. Right? You can move everything but the 4 to the other side. It doesn't really matter which way you want to do that. So let's find our gradients. Gradient of f is 2x, 6y, and negative 1. Gradient of g is 1, 1 minus 1. Right? So what we want to use then is gradient of f at that specific point, 217. This is going to be 4, 6 minus 1. And gradient of g at 217, well, there's nothing to plug in, so it's still 1 minus 1. Right? Now that we have these two, and we know both of these are perpendicular to the curve, if we take their cross product, that must be parallel to the curve. So that's going to be our direction vector for the line. So v is going to be the cross product of these two things. Oops. So this is I, j, k, 4, 6 minus 1, 1, 1 minus 1. Do this cross product, we're going to get negative 6 plus 1. Going to get negative 4 plus 1. And we're going to get 4 minus 6, parentheses. So this is minus 5, 3, and minus 2. So that's our direction vector. Now we just pop that into the formula for a line. So the tangent line we're going to use our old trusty formula here. L of t equals P plus TV. Say that L of t will be, our point is 2, 1, 7 plus t times this direction, -5, 3, -2. Right, and there we go. That's it. So the key use here, or the key point of this problem, is understanding what the gradient is doing, right? It's being perpendicular to the surface, and if there's anything you can take away from gradients, it's that, right? They're very useful for they're perpendicular to level sets, to level surfaces, level curves. They're very intimately related to, rates of change because of that. So if there's one thing you can remember about a gradient, remember that it's perpendicular to level curves. That's by far the biggest use of it, or the biggest driving concept behind the usefulness of the gradient. Right? So that's all the problems. Let me know if you have any questions. Otherwise, have a good weekend. Hope you all are doing well, are staying safe, and you and your families are all right. Yeah, take care, and we'll go for round 2 here in about 10 minutes. See you next time. All right, hello. That go away. All right. So, we got several problems on the gradient and rates of change and many uses of the gradient, which is going to be a hugely important tool for us next week especially. So let's go ahead and get started with some of these problems here. All right, so problem 1. All right, so problem 1, part 1. We have this function, f of xyz is x squared yz minus xyz cubed. Right, and each of these examples in problem 1 here are going to have 3 parts to it. We want to find the gradient, we want to evaluate the gradient somewhere, and then we want to find the rate of change in a certain direction. All right, so let's go ahead and get started with this one. All right, so computing the gradient. Remember, all we're doing here is just taking all the partial derivatives of the function and lining them all up in a vector. So take the derivative with respect to x, we get 2x yz minus yz cubed. Take the derivative with respect to y, we have x squared z minus xz cubed. And take the derivative with respect to z, and we have x squared y minus 3xy z squared. Okay. Next, we want to evaluate it at the point. Let's see. The point P equals 2 minus 1, 1. Right. So, no big... All right, then. No big surprise here. All we need to do is just plug in these numbers for x, y, and z. So when we plug that in, we're going to get 4 plus 1. Sorry, I just have to check. Did I do that wrong earlier? -4. Oh, I did this one wrong. I thought that answer felt different. All right, plug these 3 into here. -4 plus 1. There we go. Thought that felt wrong. Let's see. Plug these numbers into here, 2 and 1. So we're going to get 4 minus 2. And plug those numbers in here. We're going to get -4 plus 6. Right? And so this gradient at 2 minus 1, 1 is just -3, 2, 2. Right? So in part C here, we're asked to find the rate of change of f at this point in the direction of this vector v, which in this case is 0, 4/5, minus 3/5. Right? Now, when we're doing directional derivatives, the most important thing to remember is we have to do the dot product with a unit vector when we want to know the rate of change of a function in a certain direction, right? There is something where we can do the directional derivative and dot product with any vector we want, and that's fine. But when we want to know the rate of change of a function in the direction of a certain vector, it must be a unit vector. Otherwise, we're going to get extra, basically scaling from the magnitude of v. So let's double check here whether or not this is a unit vector, and if it's not, make it one. So magnitude of v is going to be 0 plus 16 over 25 plus 9 over 25 Right, well, that's 25 over 25. And so we're just going to get 1 there. So this is, in fact, a unit vector. All right, so the directional derivative in the direction of v of f at the point 2 minus 1, 1, this is going to be the gradient of f at this point, dot product with v. Right? And so this is -3, 2, 2, dot product with 0, 4/5, minus 3/5. Right? And when we compute this, we wind up with 0 plus 8 over 5 minus 6 over 5, so 2/5. Right? So not all that much going on in the problem here. But any questions? All right, cool. Let's go on to the next one here. Problem 2. I need to switch back to black here. It's problem 2. Here we have f of u comma v is u squared e to the minus v. Okay. So let's do these in the same order here. We want gradient of f, which is, again, just going to be take the derivatives of f with respect to the variables of the function in the same order they're listed here. Right, so differentiate with respect to u, and then with respect to v. Right? So again, we're just listing out all the first derivatives of the function. All right, so once we have that, we can evaluate it at the point 3, 0. So gradient of f at 3, 0 is, so we get 2 times 3 times 0, 1, 6. This is -3 squared times 1, so -9. Right? Part C, we want to do the directional derivative in the direction of 3i plus 4j. Right? So, well, we should always check, is this a unit vector? I think the answer is kind of obvious, but regardless, if it's not a unit vector, we're going to need the magnitude anyway. So it's always a good idea to just compute the magnitude of this vector. So magnitude of v is going to be square root of 9 plus 16. So that's 5, because that's square root of 25. So when we compute this directional derivative, we need to compute it in the direction of v hat f of 3, 0. Remember, this is going to be gradient of f at 3, 0 dot product with the unit vector in the direction of v. So that's v divided by magnitude of v. Right? Because remember, this thing here, this is what I was calling v hat, the unit vector in that direction. Right? So write this stuff down. So we're taking our vector v and we're dividing it by 5. It's 3/5 and 4/5. And so when we compute it, let's see, we have 6 times 3/5 is 18 over 5. Minus 9 times 4 is 36. 5. So -9 times 4/5 is that. And so we have minus 18 over 5. Right. Any questions there? Cool. So let's look at the last one here. F of xyz equals x y squared arctangent of z. Right? And actually, I'm going to let you guys think about this one first. Oh god. My headphones are apparently way too high in volume there. All right. So let's see, 2, 1, 1, and v is 1, 1, 1. Okay, so go ahead and try those same 3 parts. Compute the gradient of f, compute the gradient of f at this point P, and then compute the directional derivative of f in the direction of v. We'll give you a second to do that, and then we'll work through it. All right. Let's go ahead and work through this one. So computing the gradient, we're just doing the derivative with respect to each variable in order. The derivative with respect to x just leaves us with y squared arctangent of z. Differentiating with respect to y, we get 2xy arctangent of z. And when we differentiate with respect to z, we're actually going to wind up with xy squared over 1 plus z squared. Right, so it's important to remember here, the derivative of arctangent. Right, this is 1 over 1 plus x squared. Right. All right. So that's it for the first part. The second part, we want to evaluate the gradient at 2, 1, 1. So we get 1 squared. Now, arctangent of 1, anyone can tell me what that is? Of course, you could use Mathematica to get this as well. So remember, arctangent of 1, we're asking, well, at what angle is tangent equal to 1? Tangent is sine over cosine, so we're asking where sine over cosine, sorry. Yep, pi over 4. Yeah, so we're asking the angle where sine and cosine are equal. So we get a pi over 4 here. All right, so let's look at the next one. 2 times 2 times 1 times, right, we know this is pi over 4. And in here, we just plug in a bunch of numbers, so 2 times 1 squared, or 1 plus 1 squared. Right? So, cool. Now we just need to clean this up a little bit. Pi over 4 here. 2 times 2 times pi over 4 is pi. And this is going to be 2 over 2, so this is 1. Right? So, now that you have that, we can move on to part C and ask, well, what's the directional derivative in the direction of this vector? Right? again, we want to check to make sure that it is a unit vector, which it isn't. We have to make it one. Right, so dv hat of f at 2, 1, 1. This is going to be gradient of f at 2, 1, 1. Dot product with v over magnitude of v. So this is pi over 4, pi 1, dot product 1 over root 3, 1, 1, 1. Okay. Right. And remember, this number here, this 1 over root 3, we can just factor that all the way out of the dot product. There's no reason to let it make a mess on the inside. So, right, so this will be 1 over root 3 times pi over 4 times 1 plus pi over, or plus pi times 1 plus 1 times 1. So the nicest you're probably going to get this to look, I mean, you can do a little more if you want, but this will be 5 pi over 4 plus 1. I'd say that's a pretty good place to stop for it. Any questions at all about these problems? It's here. All right, excellent. Now let's look at problem 2 then. So the core idea behind problem 2, remember, comes down to, well, I want to put a u here for a unit vector, that the gradient or the directional derivative in the direction of a unit vector, right? So this is gradient of f dot u. And when we interpret this as, interpret the dot product instead of as in that component form, we use the geometric understanding of it. We're going to have that that's magnitude of the gradient times magnitude of u times cosine of the angle between them. Right? And, well, u is meant to be a unit vector, so no reason to keep that magnitude of u there because it's just 1. And the key thing to remember is cosine, the biggest it ever gets is 1. And so when theta is 0, that's when cosine is 1. And that theta there is supposed to be the angle between these two vectors. So this directional derivative gets as large as possible when we differentiate in the direction of the gradient. And as it would turn out, that the actual numerical value, when it's as large as possible, is just magnitude of the gradient. So, using that, we can answer this question of finding the maximum rate of change of the function at any specific point. We just find the gradient there and take its magnitude. So f of xy is 4y square root of x at 1, 1, or 4, 1. I did the same thing earlier. Right? So this is saying, in what direction do we have to move to see this function change as quickly as possible? Right? So the graph of this function is some kind of 3D surface. So it's really saying, like, if you imagine it as kind of like the graph of it kind of as a mountain range, and you're standing at a specific spot, it's sort of asking, well, what direction goes up at the steepest rate, right? That's sort of a physical meaning of it. So let's do our usual gradient. So we gradient this, we're going to get 2y over square root of x. We differentiate this with respect to y. We're going to get 4 square root of x. So gradient of f at 4, 1. This is going to be 2 times 1 over 2, so 1. And this is going to be 4 times 2, so 8. And there we go. So the max rate of change is just the magnitude of this gradient at 4, 1. Which is going to be square root of 1 plus 64. So that's 65. Square root of 65. And there's not a whole bunch more to say than that, really. Not a whole bunch more. For computing that number, there's no way to simplify it. So the important thing here is just sort of pointing out that this gradient has huge geometric significance for functions, right? It's a very, very useful object. All right, so go ahead and try this on your own for a second for the next function, and then we'll work through the solution of that. So this function at 8, 1, 3. Take a second to do that and see how it goes. How are we doing here? Any questions about it before we write out the solution? All right. Go ahead and get started here. So gradient of f, right, differentiate with respect to x. We get 1 over y plus z. Differentiate with respect to y. We're actually going to get negative x over y plus z squared. And we actually get the exact same thing when we differentiate with respect to z. It's kind of neat. All right, so gradient of f at this point, 8, 1, 3, is going to be, was it 1 over 4 minus 8, comma, minus 8 over 4 squared, comma, minus 8 over 4 squared. And this is 1/4 minus a half minus a half. And so we want the magnitude of that. 8, 1, 3. Right? And let's see, we're going to get square root of 1 over 16 plus 1/4 plus 1/4. All right, so this winds up being square root of 9 over 16, which is 3/4. Any questions about that one? All right. Yeah, so hopefully those two problems haven't been too bad. They're pretty the computations are pretty straightforward. But again, what I really want to emphasize about the gradient here is sort of, its geometric significance, right? It's giving us this direction that we're going to change the greatest. And this has to do with how it works with level curves, right? We want to sort of move away from level curves as quickly as possible to change our value as quickly as possible. And it works out that, the level curves or level surfaces or level sets in general, when you go up in dimensions, the gradient is always perpendicular. At every single point, the gradient is always perpendicular. Unless your function is like singular there. Then you could, have like a gradient of 0 or something. Have some kind of weird thing going on with your function. If your gradient 0, it's a critical point of the function. All right? And that'll be a very big deal, actually, starting next week. We'll talk about critical points, and the gradient, as it turns out, is how we detect those. All right. So, problem 3. Okay. So we want to find the equation for the tangent plane to, I don't know why I was about to write a 3 there. The tangent plane to this surface at the point 1, 1, 1. Okay. So tangent planes, much like tangent lines, are meant to give sort of like the kind of like a linear approximation of your surface, right? So there's some interesting stuff. I don't think we'll actually say a whole lot about it. I think we'll talk a little bit about this approximation idea toward the end of the semester when we do Taylor series. But the key thing here is, when we want to get the tangent plane, remember, we need a normal vector to the plane, and we need a point on the plane. Well, of course, the point on the plane is obviously this, because that's where we're trying to find the tangent plane at. But this is, again, where the gradient being perpendicular to the surface comes in to tell us information about it. Right? So we need to understand this surface here as a level surface of something. So we're going to take it and shove it all to one side of the equation so we can call it a function. So we'll shove everything to the left. Right. And then our our specific level surface would be when that's equal to 0. Right? So gradient of f. Right? This is how we're going to get our hands on the normal vector. Gradient of f would be 4x cubed. This is gone, this is gone. This turns into negative 6x y squared z squared. Okay. The next step, differentiate with respect to y. 4y cubed minus 6x squared yz squared. And differentiate with respect to z. 4z cubed minus 6x squared y squared z. All right, so that's our gradient. Gradient of f at 1, 1, 1 is, well, we're going to take these values, 1, 1, 1, plug them on for x, y, and z. So it's going to wind up that we get 4 minus 6 in all of the slots here. And so get that. Okay. Which is great. Right. So now we have our normal vector to the surface at this point. Now, one thing I want to point out is if we're only interested in finding the tangent plane, we could, of course, take any vector parallel to this. Namely, you could use 1, 1, 1 if you wanted to. Go away. Go away. Right, so namely, you could use 1, 1, 1 if you so chose. Right. But I'll stick with using the gradient. So the tangent plane itself, well, the equation for it is, well, take your gradient at some point, dot product with x minus 1, y minus 1, z minus 1. Right? So remember, it's the equation for a plane is the normal vector dot product with xyz minus the point that you're trying to find the plane at. Right? So I have -2, -2, -2, dot product with x minus 1, y minus 1, z minus 1, 0. And really, it's perfectly fine to stop here. Like, this is the equation of the plane. This, shows that it involves the gradient. You know how to construct a plane. This is really the most important information here is this stuff. Right? But now, if you wanted to, you could go through, compute this dot product, and you'd wind up with this equation, which of course is also fine. Right? So, any question at all about finding the tangent plane? I'm out of. All right. Let's go on to the last question here. Problem 4. Right. So problem 4. Right, here we have two surfaces. We have the paraboloid and the plane. We have these two, and they intersect in some curve C. Right? So what does that look like? Let me swap over to Mathematica here. So here I've graphed the two surfaces. The paraboloid is the orange thing here. It looks a bit cut off on the sides here because of the plot window. But that is in fact a paraboloid. Okay. And the blue one here, this is the plane, z equals x plus y plus 4. Okay. So if we look at their intersection here, this oval here, this ellipse, this is that curve C. Right? This intersection here between the two. That is C. Right? So what we're doing is we want to say at the point 217, so somewhere along this curve, see 217 would be probably somewhere in here toward the edge of the ellipse here. Right? So somewhere on there, we want to find the tangent line to that curve. So how does that work? Well, the important thing to remember is that the curve lies in both of those surfaces at the same time, right? So remember how the gradient is perpendicular to the surface. since the curve lies in both of those surfaces, the curve C is going to be perpendicular to both gradients, right? And then using that fact, you should be able to reconstruct the tangent vector to that curve. So I want to find the tangent line at the point 217. Right? So I'll give you a second to try and work that out real quick. And I will be right back. All right. How's it going? So, look at the last bit of this problem here, right? So we need to view these surfaces, or these surfaces as level surfaces of something. So for the paraboloid, again, we're just going to push everything to one side. So the paraboloid, we could say, well, it's a good idea to write down variables for this. Right, so this would be x squared plus 3y squared minus z. And the surface we'd be looking at is when that equals 0. And then g of x, y, z. This would be, take the plane equation here and move everything to one side. So we could say x plus y plus 4 minus z. Right, and then that would equal 0. Right. So take these, take your gradients. Gradient of f is 2x, 6y, negative 1. Gradient of g is 1, 1 minus 1. And now we want to evaluate them at 217. Let me make that look less like 17. Right, evaluate it at this point. The gradient of f at 217 is 4, 6, minus 1. Gradient of g, oops, these are supposed to be capitals, at 217. Well, there's no variables to plug in here, so this is not going to change. Right. So now that I have these two, and they're perpendicular to the surface at 217, in particular, they're both perpendicular to the curve C there. What would I do with them? to create a vector that's tangent to the curve. Remember, the curve is going to have two perpendicular directions and one tangent direction, because it's sort of a one-dimensional object. So what would I do with these two things to create the tangent vector? Tangent vector is going to be perpendicular to both of these gradients. So the thing I need, yeah, we want the cross product. So let's take that cross product. IJK, let's say 4, 6, negative 1, 1, 1, minus 1. Do this cross product, we're going to get negative 6 plus 1. Let's see, do this one. We're going to have negative of negative 4 plus 1. And 4 minus 6. So this is going to be minus 5, 3, 2. Right? I think I did that right. Yep, should be good. Right. And then I have my direction vector for the tangent line here. I have my point on the tangent line, which is 2, 1, 7. So the tangent line, right, we're going to use our trusty old formula for a line, b plus tv. And so the tangent line for us in this situation is 2, 1, 7 plus t times minus 5, 3, negative 2. Right? And that's that. And just as a reminder, because you'll, I think, see this in the homework, it asks about the parametric form of this. Just a reminder what that is. We combine this all together. Plus 3t, 7 minus 2t. And then your parametric form is just going to be, you know, these are x, y, and z. So x is 2 minus 5t. Y is 1 plus 3t. Z is 7 minus 2t. Right, so it's kind of the, you know, the same form we were looking at for the solution to a system of equations before we split it up into those vectors. I honestly really think this is always the better way to look at it, but you know, what I think is better and the ways WebAssign wants the answers aren't always the same thing. All right. So that's all the questions from the problem set for today. Were there any questions anyone wanted to ask? So the final, I'm still thinking, trying to figure out exactly how to do the final. One idea I'm actually floating right now is doing some kind of like live sign up thing. So like giving you some part to do at home without without any live component, just like maybe a timed WebAssign assignment, some questions that have a while to, respond to and submit. I'm also thinking of, having maybe a question or two where we'll set an appointment and you'll have to, explain the problem to me or something like that. Just so I can sort of check, like, how well do you understand certain concepts? Because, that kind of stuff doesn't come through as well as I would hope. Sign itself. So I might do something like that for the final. I think what I'm leaning toward for exam 3 is actually replacing it with a few different timed WebAssign quizzes. So basically taking an exam and chopping it into smaller pieces and then just sort of distributing that over a couple weeks. That way you can sort of do it piece by piece, or little bit at a time. You can do them all at once if you want as well. But WebAssign has a feature where I can say, like, hey, you can have, an hour to do this assignment. And so whenever you open it, it starts counting from that time. So that way it doesn't sort of put time zone restrictions on anyone. And I think that's likely what we're going to do. I want to start like writing out details of that, which is the plan for today. So hopefully that doesn't, or at least hopefully those ideas kind of make sense. It's maybe slightly vague still, but yeah, it turns out this is a lot harder to figure out how to give a meaningful exam than I thought. Yeah, I think that's the best I can say at this moment. Any other questions? Mhm. So probably the way this would go is you'll have like, I think my idea that I was thinking is, giving a certain number of submissions and each wrong answer counting down a certain percentage. That's probably the best way to do it, since I can utilize the feature that WebAssign lets you submit multiple times, and we can kind of try to leverage that to figuring out, like, okay, that was wrong, how do I correct the answer? But so I was thinking something like that. Also something like, if you attempted the problem, you'll at least get some points for the problem, whether it's right or wrong. But yeah, partial credit becomes a lot trickier. And it not the ideal situation. But hopefully something like that, just to make the questions not all or nothing, kind of helps with that a little bit. I'd really like to, some of the questions that WebAssign has do require you to kind of expand a bit more step by step, so those could be helpful in terms of doing partial credit as well. Which I think we probably don't get as many of those in the homework because it gets mad at you when you try and create an assignment and you want to allow multiple submissions, but the question has multiple parts to it. Yeah, so something like that could also help with at least trying to emulate partial credit. I think that's all I could say about that at the moment until I actually try to make some of these. In fact, I've been thinking about trying to sort of like make a sample sort of WebAssign quiz that's not worth anything grade wise, but to sort of send out to everyone and say, hey, this is kind of what to expect when it comes to the quizzes, exam stuff. Are there any more questions? All right, so either sometime today or tomorrow, I'll be posting up the next round of lectures and assignments on WebAssign. And then, yeah, we'll get ready to get started on sort of the last bit of the differential part, right? Which is all the first, what's kind of the analog of the first derivative test and optimization stuff. And then we're off to integration, right? So with that, unless anyone has any last question here, thanks for watching. Thanks for coming in. I hope you're all doing well and your families are doing well as well. And yeah, take care. Have a good weekend, and I'll see you Monday.